Okay, ladies and gentlemen, welcome to the last chapter of the semester. You finally made it here. And it turns out that this chapter is the culmination of pretty much every other chapter that we've talked about up to this point. And it turns out that for our textbook, this chapter has a very misleading title. It's titled The Big Bang. And that makes it seem like it's going to talk about only the Big Bang. Well, that's not actually true. This chapter should really be called Cosmology, because it's about the universe in its entirety, the cosmos, in its past, aka the Big Bang, but also at the very end of this chapter, its future, as best as we can predict. But still, let's go ahead and kind of start talking about this chapter in terms of the past. Well, we know from Hubble's law that all of the galaxies that are far away from us, they are moving away from us due to the redshift that they possess. All right, well, it turns out that if we kind of take that to its logical extreme, if all distant galaxies are moving away from us or moving away from each other, because it doesn't matter where you look, they're all moving away from everybody, then what does that imply about the past? Well, if objects are moving away from you now, that means that in the past, they had to be closer to you as a consequence. If you take that back far enough in the past, that means that in the context of, for example, like an explosion, when an explosion occurs, the debris is pushed outwards away from the source, such that if you kind of rewind the video in your head, it all kind of coalesces into a single point of the explosion. And we say that the same thing kind of occurs here in the context of the cosmos, the universe. Galaxies are kind of moving away from each other, kind of shown here in the top frame of this picture. But if we kind of go down in decreasing time, back in time, everything was closer together, until everything was essentially on top of each other at a single location that we call a singularity. Kind of like, for example, how we called what formed a black hole, the central object, a singularity as well. So based upon Hubble's law, we were able to show that, again, the speed, the recessional speed of a galaxy is related to how far away it is from us, where the symbol of h subscript 0 was what we call the Hubble constant back at that time. But it turns out that in physics, we also know that speed is proportional to distance in time. We actually have used that equation as well. So this v here, it corresponds to speed. And again, according to physics, speed is just distance over time. Well, what I want you to kind of notice is that from combining physics with astronomy, I have distance on both sides of my equation. So that means that I can really kind of cancel it out. And if I cancel it out, I can basically flip the fraction. I can invert it such that I don't get 1 divided by t. I get t divided by 1, or just t for simplicity. And by flipping the left-hand side to get t on top, I have to flip this to put it on the bottom of its own fraction. And what this basically means is that this idea of t, this corresponds to the age of the universe. So d is the distance of the furthest galaxy that we can see with our telescopes. This is how long that distance, this is how long that the galaxy has been able to move away from us. Again, this is the distance that the galaxy is away from us. This is Hubble's constant. So what we say right here is that 1 divided by the Hubble constant is the age of the universe, sometimes called the Hubble time, kind of a weird thing. But we say that our universe is 1 Hubble time years old. Converted into tangible years, that corresponds to roughly about 13.6 billion years old. So our universe is a fairly old universe. Good for us, turns out, but fairly old by human standards in this case. Well, it turns out that this idea of how old the universe is can tie into the cosmological principle in a very interesting way. So for example, we know from the chapter 28 idea of the cosmological principle that light travels at a finite speed, 300,000 kilometers per second, 150,000 miles per second. Well, we know that distant galaxies, quasars, for example, are very far away from us. So again, based upon the idea of the cosmological principle as well, We know that light takes a certain amount of time to get to us, the idea of look back time as well. But this creates an interesting consequence. Because the universe is only 13.6 billion years old, that means that there is a cosmological horizon, in the sense that there are galaxies here that are far away from our galaxy, and they're emitting light that takes a certain amount of time to travel to us. But a galaxy that is at this location on the cosmological horizon, when it first formed long ago in the past, it produced light that has now just barely gotten to our galaxy. So we can just barely see the light that formed from this galaxy 13.6 billion years ago. I'm being a little bit dramatic. It didn't quite happen that way, but in this melodrama that I'm giving to you, we can barely see the flash of light from this young galaxy 13.6 billion years ago. What this means, though, is that there is the possibility of other galaxies beyond the cosmological horizon that exist, but we cannot see them because not enough time has gone by for light to be able to travel that large enough distance to get to us in the first place. So kind of like you see in this picture here, this is light being emitted by a galaxy, but because it is beyond the cosmological horizon, then it takes more than 13.6 billion years for that first ray of light to get into our telescope. So therefore, we have no idea that it exists, and therefore that location on the celestial sphere, that pinpoint location on the celestial sphere, appears black in color. Once enough time goes by, then we will be able to see light from that object. So the way that we can think about this is that the cosmological horizon is expanding over time, because the more time goes by, the further back we can see in the universe. And therefore we can see more distant objects as they were forming long ago in the past. But this is a weird idea, because we know from the cosmological principle that the universe is infinite in this case. But we can't see that infinite universe because we are bounded by a cosmological horizon. There might be galaxies beyond the horizon that exist, maybe even have life, but because they're too far away from us, we can't see the light from those galaxies, so they're invisible to us in this point. They are beyond the observable universe, as we sometimes call it, kind of like you see labeled right here on the right-hand side. Crazy, but we need to keep that in mind going forwards. Now, this does create a small problem, though, with the cosmological principle. And we're going to go ahead and kind of hit upon that dilemma in the next couple slides. So in the course of revealing the dilemma, we have to actually kind of go back to the very beginning of our universe, aka one Hubble time in the past. And we're going to be, again, focusing on cosmology, the study of the cosmos, the study of the universe as a single entity. And what we're going to say about that one is that the universe started off as a singularity. And back in chapter 24, when we talked about black holes, we said that a black hole, the object itself, was a singularity that had an event horizon, it had a photon sphere, and kind of other structures that were surrounding it. But it was a singularity. We said that a singularity was a point of infinite density. So a lot of mass packed into zero volume. Seems like a weird thing, but that's how we define a singularity, is an object that has an infinite physical property that makes no darn sense. It's kind of like having infinite energy. Just doesn't make any darn sense, so it's a singularity in that case. But the Big Bang occurs. Now, why does it happen? Have no idea. But the Big Bang occurs. The universe forms. Space-time is created. And there is a release of radiation, light in effect, throughout space-time. Immediately after the Big Bang, in the first era, as we call it, of the universe, the first era of the universe is a very small period of time. How much time are we talking about? Well, it's called the Planck time, spelled in this way after Max Planck, the physicist. And what he kind of discovered is that in this very small period after the Big Bang occurred, the universe could not be explained by the laws of physics. It was beyond their explanation. And even into modern day times, 2020, if you try to go between the Big Bang and the Planck time end, this idea of 10 to the negative 44 seconds, and again, using powers of 10 notation, negative exponent, very, very small. And we're talking negative 44, so that's a really small period of time. But in between t equals 0, the Big Bang, and t equals 10 to the negative 44, physicists have no idea what happened, because the laws of physics just cannot explain what is happening in that extreme of an environment. After the Planck time, we have a pretty good idea what happens. But before the Planck time up to the Big Bang in this very small duration of time, no idea, complete mystery. Still trying to figure it out, but I'm personally pessimistic about it. So we're going to go ahead and focus on now the early universe after the Planck time. And we're going to focus on the first kind of true era in this case, the first true age. And to understand what's about to happen in our universe, we have to kind of go back to basic behaviors of gases and plasmas. And what we said is that back in the past, kind of like we talked about, for example, with the sun and the formation of our solar system and so on and so on and so on, what happens as a gas expands? Well, there are two things that I'm looking for. So for example, as a gas expands, what happens to its density? Well, the mass doesn't change because it's the same number of particles, but as a gas expands, what's changing? Its volume. Well, same mass, but now expanding volume, larger volume. What does that mean about its density? In a similar sense, when a gas is expanding, how does that affect its temperature? Well, it turns out that for both of them, the variables decrease. As a gas expands, its density decreases because it's occupying more space, but has the same number of molecules, the same number of particles, the same number of atoms and compounds and things like that. But it occupies larger amount of space, and it also has less energy per molecule, aka a lower temperature in this case. And that's a phenomenon that has occurred progressively because our universe is expanding thanks to Hubble's law. And this kind of shows us a graphical representation of what the density and the temperature of our universe looked like on very large scales at a time of 0, aka the Big Bang, to a time of, again, 13 billion years old, aka modern day times in this case. So when the universe was very, very young, about 17,000 years old, the temperature of space-time, the temperature of the universe, was about 100,000 Kelvin, which is fairly impressive. Okay. Now, if you kind of fast forward that to 13 billion years old, roughly about modern day times, the temperature of space-time is only about 3 Kelvin. So the temperature of the universe, not stars, not galaxies, not people, but the temperature of space-time itself is only 3 Kelvin, very, very cold, indicating a very kind of initially fast, but then a very, very slow, gradual cool off to a modern day cold temperature. In a similar sense, in the very beginning, the universe was very, very high density, kind of like that computer simulation that I showed you at the very end of chapter 28 with that kind of aqua light blue color. Very high density in the beginning, but as things coalesce, as we start to form galaxies and stars and molecular clouds and protogalactic clouds and things of that nature, the density of the universe decreases until it kind of decreases to 0.1 atoms per cubic meter, which is actually quite a laughable amount, but that is the current amount of density in our universe, again, sampled over a large volume of space, aka our supercluster, in effect. But both of these variables are going to be important because it turns out that as something cools down and as its density decreases, its behavior becomes more predictable and more understandable in terms of human association. So what do I mean by that? Well, it turns out that first things first. With the cosmological principle, we know that the distribution of mass, aka matter, galaxies, everything that we see nowadays, is homogeneous and isotropic. But the problem, though, is that the cosmological principle, it implies that the energy in space-time, aka its temperature, is also homogeneous and isotropic. Here's a small problem, though. A hot plasma in physics isn't homogeneous and isotropic. A plasma in physics has hot spots and cold spots. But the cosmological principle states that our universe on large scales is homogeneous and isotropic, both in terms of mass and in terms of energy/temperature as well. So to explain this dichotomy, because the Big Bang says that we were kind of formed from a giant release of energy, and that energy wasn't really uniform, but according to the cosmological principle, it kind of has to be. Then the idea that was kind of proposed to explain how the universe could have evolved to be homogeneous and isotropic very quickly is something called the inflation theory. Now, this isn't the only theory that has been proposed to explain this dichotomy involving the cosmological principle, but it's the one that is most popular in modern day astronomy. And what the inflation theory kind of proposes, kind of like its name implies, is that the fabric of space-time underwent a brief but rapid expansion. And that brief but rapid expansion caused the density of our universe to decrease substantially, and also to cool down substantially as well in a very short period of time, which allowed the temperature, aka the energy and therefore the mass within the fabric of space, to be more homogeneous, to be more isotropic, to be closer in truth to what the cosmological principle predicts in the first place. So it's a very kind of weird theory, but it's one that's introduced just to make the observation of the cosmological principle fit with the idea of an expanding universe due to the explosive release of energy from the Big Bang singularity long ago in the past. Now, as the universe is cooling down during inflation and even kind of afterwards as well, you get to what is called the force freeze-out. And the force freeze-out, it deals with something called the GUT, or sometimes called the gut. And what is the GUT? Well, it's an abbreviation for the Grand Unification Theory. It is a theory in physics that tries to unify the equations of all the different forces in the universe. And big surprise, it's a tough thing to do. So it's taken 100 years for us to kind of eventually get it down to a point where we're close to the truth. Not technically there, but we're close to the truth. But it turns out that according to this idea of the Grand Unification Theory, the universe, aka space-time, is filled with radiation. And as this fabric of space-time is expanding due to the explosion, quote unquote, of the Big Bang, that cooling down of radiation is occurring because the fabric of space is expanding, aka the idea of redshifting, like we talked about from before. We talked about this idea of cosmological redshifting, how mass or the kind of inflation of space-time, the stretching of space-time, can cause light to be redshifted. And the redder the color of light, the cooler it has, the less energy that it has in the first place. Now, the funny thing, and this gets a little bit in circular logic, which is never a good thing, but here's the funny thing about the expansion of the universe. Just like in this balloon, how it's expanding, well, something has to cause the balloon to expand in the first place, aka you have to blow into it on the bottom. It doesn't work that way for the universe, but here's how it works. When light undergoes redshifting, its color is redder due to the expansion of the universe that it's moving through. That means that the light from the redshifting, it's become redder in color, lower in temperature, it has lower energy. Where did the energy go? Into the fabric of space-time. What does that energy do? It expands space-time. So the expansion of space-time creates redshifting, which in turn gives energy for the expansion, which creates redshifting, and it's basically just a never-ending process. Very kind of weird, but very, very cool as well. But as this process of expansion is occurring in the fabric of space-time, the forces of gravity, electricity, magnetism, and then the nuclear forces that hold the nucleus of the atoms together, they eventually become distinct forces. Prior to this, the universe is too hot and too dense, such that these four forces are indistinguishable from each other. But as the universe cools down, the four fundamental forces of the universe, gravity, electricity, magnetism, and the nuclear forces, they become distinct, and therefore they freeze out due to this cooling down of the universe in this case. It also turns out that as the universe is cooling down, we start to have the first matter particles being formed and also being destroyed equally fast as well. I talked a little bit about this in chapter 24, when we talked about black holes, Hawking radiation, matter and antimatter. But it turns out that within the universe, matter can turn into energy, and energy can turn into matter, thanks to Einstein's equations, over very brief periods of time. So figure A, what's called pair production, is because you're producing a pair of particles, a proton and an electron, just from two radiation waves interacting with each other. In a similar sense, when a proton and an electron collide with each other, they can totally kind of annihilate and kind of produce energy as well. But for us, we're not going to focus on proton and electron, which is more for particle physics. We're going to focus more on matter and antimatter in this case. So energy can be converted into matter and antimatter. Matter and antimatter, when they collide, can be converted into energy as well. And this is occurring spontaneously. This is occurring kind of very, very frequently in the very young, very, very hot, high density universe, such that we say that during the early universe, up to this period of time where the forces are freezing out, we say that the universe is radiation dominated, because there isn't really a large population of matter in the universe yet. It's primarily in the form of radiation, aka light from the Big Bang. So there is a little bit of matter, but not very, very much. It coexists with copious amounts of radiation as a soup, in this case, as we're going to call it. Soup implying that we have particles, very few, and a lot of radiation coexisting in the very young universe at this time. Now, the universe keeps expanding, the fabric of space-time keeps expanding, and the temperature keeps dropping until we get to a point, or until we get to an era called recombination. Now, somebody always asks me in class, well, if we have recombination, what the hell is combination? Well, odd choice of words. There is no combination. In the universe, we only have recombination in this case. But how recombination works is that this idea of matter and antimatter being created and then destroying themselves, being created and then destroying themselves, that rate slows down such that we start to form stable particles, protons, antiprotons, electrons, anti-electrons, things of that nature. And eventually what happens is that we start to have the formation of different isotopes of the hydrogen atom, and also to a very, very small extent, the helium atom as well. What was the ratio? Well, pretty much 99 to 100, 99 hydrogens to 1 helium atom being produced in this case. And it's really the nucleus of the atoms that form first, but eventually the electrons slow down enough to where they actually become captured by the electric force of the kind of nucleus of an atom to form the actual atoms themselves of hydrogen and helium. So the era of recombination, it occurs roughly about 300,000, give or take, years after the Big Bang singularity. So these kind of atomic hydrogen and atomic helium atoms, this is kind of before recombination, where you have matter and antimatter producing, annihilating, producing, annihilating. It's a big nasty soup. But after recombination, you start to form hydrogen and to a lesser extent helium atoms that are stable. And you still have light, you still do have light existing, but there's much less light in the universe to where it can travel freely through space-time without interacting with other rays of light, other kind of waves of light, to kind of undergo the creation of matter and antimatter in that case. So starting with recombination, we start to go from a radiation-dominated universe filled with lots of light and very little mass, to now having a matter-dominated universe, where our universe is filled primarily with matter and not necessarily radiation in comparison. But one of the unanswered questions about cosmology is what's called asymmetry. And when they say that phrase, what they're really referring to is antimatter asymmetry. Well, what do they mean by asymmetry? Well, asymmetry just means a difference between two things. So for example, in class, we talked about the context of symmetry. If I were to kind of take a machete and kind of cut you down the middle, left side of you would have one ear, right side would have another ear. You have symmetry in that sense. But if I were to kind of take my machete and kind of cut your head off, well, you would have your head on one side of your body, but not a head on the bottom half of your body. It would be missing in that case. So you have asymmetry in that context. It turns out that in the early universe, before recombination, radiation, light, was forming matter and antimatter in a 1-to-1 ratio. So before recombination, matter and antimatter existed 1-to-1, 50% and 50%. But all of a sudden, after recombination, the universe becomes dominated by matter. So where did the missing antimatter go? We don't know. We have no idea that everyone agrees upon. So there is an asymmetry in the amount of antimatter in the universe. Where did it go? Did it evolve? Did it just disappear? Did it go into another universe? We have no clue whatsoever. Because long ago, before recombination, there should have been a crap ton of antimatter, but now in the universe, antimatter is extremely scarce. We find very little at all when we look at our telescopes. And for the amount of stars and galaxies that we see in the universe, there should be an equal crap ton of antimatter, but don't see it, can't find it, doesn't exist. So this is one of the big questions about the history of our universe. Where did the antimatter go when recombination occurred 300,000 years in the past? Well, it turns out that this idea of recombination, it produced a very interesting phenomenon in astronomy. And it was discovered by these two gentlemen named Penzias and Wilson. And these were two engineers who worked at Bell Labs. I believe this is Penzias and I believe this is Wilson, but I could be wrong. And what they did is they were doing experiments at Bell Labs. And Bell Labs is basically, it used to be associated with the Bell Telephone Company, but shortly thereafter they kind of diverged, and now they kind of focus much more on purely scientific industrial research. Most people who win the Nobel Prize in physics, I'd say at least 75% of them come from Bell Labs. So if you work at Bell Labs, things are probably going your way. But nonetheless, these two very famous physicists, they were conducting research with microwave radiation shortly after World War II. And what they discovered is that when they were doing their experiments, they discovered noise. They discovered unexpected signal, unexpected microwaves from their very bizarre shaped kind of antenna that you see right here. Kind of looks like an old-fashioned earphone that you would attach to your ear to hear. And kind of weird enough story, when they discovered these microwave signals that should not have been there when their kind of antenna, their telescope was turned on, they first thought that, okay, well, maybe it was a source of microwaves nearby. So they went to the nearby town and sure enough, no microwaves there, all right. And then they thought, well, you know what, maybe it's from bird droppings on the antenna. So they cleaned the antenna meticulously, did the experiment again, and they got the same noise, the same signal of microwaves coming into their antenna at all times. So they postulated and they thought about it and they thought about it. And then one of them remembered reading an article from an astronomer who proposed that during the era of recombination, when the universe became matter dominated, that light would now be free to travel through the universe. And that light could now explain this radiation that they're detecting in the nighttime sky. And the reason why they were kind of confident that they had discovered something called the cosmic microwave background, because this microwave light that they were getting with their telescope, it was distributed across the sky uniformly. So that means that it couldn't be caused by an isolated object like a star or a galaxy or a quasar or even anything like that. It's essentially the same in all directions. So this is a false color image taken of our galaxy, taken of our nearby supercluster basically. And it's kind of shown in a false color because we're talking about microwave light. The color of dark black blue corresponds to minimal microwave light. The color of red corresponds to strong amount of microwave light. And what I want you to notice is that it's essentially uniform. I mean, there are hot spots and cold spots, granted, but still, there isn't a giant solid chunk of red over here. There isn't a very large section of yellow only over here. The blue, green, yellow, and red colors are more or less uniformly spread out. And that could really only occur from an explosion-like event. And because we're talking about our entire supercluster, that could really only correspond to the Big Bang singularity. So this microwave radiation that these two engineers discovered is the remnant of recombination when when radiation light could travel freely through space-time without being converted into particles and therefore kind of disappearing in that sense. So this cosmic microwave background radiation is basically the afterglow of the Big Bang. It is the light that was produced from the Big Bang, because light doesn't really kind of get stale and age, but that light could only be seen after recombination occurred and the density of the universe was low enough to where light could travel uninterrupted through space-time, through the universe in the beginning. Okay, so after this kind of discovery of the microwave background, this idea of recombination, fast forward, and now we're going to go ahead and start to focus on larger scale behaviors, this idea of the first generation. So what do I mean by first generation? Well, because we're now able to form hydrogen and to a lesser extent helium, as time goes by, we're now also able to form more complicated elements, not just hydrogen and helium, but maybe, for example, things like dust that we talked about from before. So we start to form our first protogalactic clouds, and therefore we start to form the first generation of galaxies in the universe. And when galaxies formed like this long ago in the past, when the universe was hot and very close together, high density, high temperature, that is ideal in terms of forming quasars. So the quasars that we kind of see right now are light from the old quasars because they've taken so long because they're so far away from us. But the first formation of galaxies also kind of corresponds to the formation of quasars as well. It also kind of allows us to form smaller structures, aka molecular clouds, and individual stars within those kind of protogalactic clouds as well. So fast forward, we now kind of form the first big structures in our universe, and we also start to form the metals, as we call them, in our universe. Now, the phrase metal isn't quite what you mean in everyday conversation. So for example, in everyday conversation, iron is a metal, steel is a metal, copper is a metal. But in astronomy, any element beyond hydrogen is a metal. I know that's a weird thing to say, but the dominant element in our universe is hydrogen. Everything else is a distant second or third or fourth or beyond in comparison. So anything that's not hydrogen is a metal. And it turns out that metals formed primarily through the process of nucleosynthesis, this idea of thermonuclear fusion, and also this idea of nova explosions as well in our universe. So it's really kind of in this era where we start to form galaxies and stars, where we start to have the periodic table of elements and all the different elements kind of form in noticeable amounts. Prior to this, the universe is just primarily hydrogen, helium, protons, neutrons, electrons, and other exotic particles, but that's it. That process of evolution, growth, expansion, cooling down continues. So roughly about 500 million years after the Big Bang, we have the first galaxies start to form, our first quasars, and then the galaxies start to form. We start to have filaments within this idea of superclusters. And now we kind of have modern day universe where things are kind of fairly spread out. Cosmological principle still applies, but things are kind of more spread out from each other, such that we can kind of clearly distinguish galaxies from each other, even when they're far away, at least as we see them in this case. So once we kind of get to the modern era, we're now going to go ahead and switch gears for the second half of this chapter, and we're going to focus on the future, aka the fate of the universe. Now, it turns out that the fate of the universe is actually quite complicated. But what we're going to say is that the fate of the universe, it depends upon the specific behavior of two competing forces. I'm using that term very kind of liberally, but two competing behaviors, attractive forces or attractive behaviors, and repulsive forces or repulsive behaviors in the universe. So for example, gravity due to mass is an attractive force, and there's a lot of mass in the universe, so we have to take that into consideration. At the same time, the explosion from the Big Bang, the expansion of the universe, that is a repulsive influence that needs to be taken into account as well in terms of the fate of the universe. So whichever force is stronger, more dominant, that will dictate the fate of the universe consequently. So how do we figure out what is the exact fate of our universe? Is it something that's attractive in nature, or is it something that's repulsive in nature? The way that we can do that is to figure out the mass density, aka the matter density of our universe. So how do we do that? Well, we deal with something called average mass density. And this is pretty much identical to the idea that we talked about in chapter 7 with density back at that time, average density. It's just that now we're not talking about individual planets or stars. We're now talking about the cosmological principle saying that matter, aka galaxies, are uniformly spread out. And what that means is that on large scales, the cosmological principle states that the density of the universe is the same. So this means that if we can find the density of our local area of the universe, like our supercluster, for example, if we can find that density, then that will allow us to understand what our fate is. So by looking at our local supercluster and by figuring out the mass of the supercluster, which is tricky, but we know from previous chapters that luminosity can help us figure out mass, so it can be done. But by finding the mass of our local supercluster and by dividing that by the size of our local supercluster, we can get the average mass density of our neighborhood in the universe. And it turns out that now that we can do that, we have to first kind of understand problems with that, difficulties with that. So according to general relativity, we know that mass creates curvature in space-time. It bends space, as we said. So what this means is that from this idea of general relativity, there is something called the critical density of the universe. And that can be calculated. And in fact, Einstein himself calculated it. And there's a very weird story about the cosmological constant, Einstein's biggest failure, but maybe it wasn't a failure, and so on and so on. But Einstein was able to calculate a critical density of the universe. And what this critical density corresponded to is a perfect balance between the attractive forces of gravity and the repulsive force of the expansion of the universe and the Big Bang explosion. And what Einstein kind of figured out is that this critical density, it had a value of 10 to the negative 26th power. So again, powers of 10 notation, 10 to the negative 26, it's a negative exponent, so it's small, so we got to take that into account. But it turns out that if we compare this critical value from the theoretical predictions to our observed value within our own supercluster, that comparison will allow us to understand the fate of our universe. What did we get? Well, it turns out that we got something that contradicted other independent measurements of the mass density of our universe. So what do we mean? Well, based upon Penzias and Wilson, they discovered that the cosmic microwave background existed, that the universe has a temperature, in effect, roughly about 3 Kelvin. Well, by working backwards from that insight, you can also calculate the average density by mass of the universe. And if you compare that number from Penzias and Wilson and others, Penzias and Wilson get too much credit, but comparing their number to the critical density, our mass density from the Penzias and Wilson cosmic microwave background is a little bit less than the critical density. Okay, so why is that important? Well, if we just look at the light from our supercluster and use that luminosity to figure out the critical density, it's actually an underestimate. We're off by about 73% of what the number should be based upon the cosmic microwave background predictions. So this creates a problem because even if we include dark matter into our calculations, it doesn't get any better. So what this basically means is that from independent observations, the critical density of our universe should be almost equal to, the mass density of our universe should be almost equal to the critical density. But if you look at mass and luminosity and dark matter, you get a underdetermination, an underestimate of that amount. So what that means is that there's something invisible to telescopes that constitutes, that makes up the missing mass density of our universe from a telescope accounting. That missing density we call dark energy. Now, it was hard enough to explain in chapter 25, and then our book also mentions it in chapter 27 as well, dark matter, what it is. But it's even harder to explain what dark energy is. All that we know is that dark energy constitutes the missing piece of our universe. And the weird thing, though, is that by looking at really old light, for example, the cosmic microwave background, there was no dark energy in the past, 13.6 billion years ago. But there is dark energy now in the modern day universe. So weirdly enough, the amount of dark energy, this weird, mysterious, hard to understand phenomenon, it didn't exist before, but it does exist now. So a big question that we have in astronomy, besides what is dark energy, is why is it growing over time? Why is almost 73% of the universe this completely unknown dark energy thing, whereas back in the past, it didn't exist at all? So in terms of dark energy, there's really not much that I can tell you that's kind of appropriate for our level of astronomy, because there's really no consensus in the community as to what it could be. It's completely open-ended in terms of knowledge. All that we know is that it does exist, but beyond that, we really don't know too much about it. I'll kind of hint about what it does at the very end of this chapter. But in terms of its behavior, it's a big question mark. It exists, but what exactly does it do and how does it work? Tougher to explain. But again, based upon independent confirmation, the density of our local supercluster, and therefore the density of our universe, is essentially equal to the critical density, but technically a little bit smaller. This is important because being a little bit smaller than the critical density, it can allow us to understand the fate of our universe in the future, but we have to be careful in how we explain it. And the first way that we're careful about explaining it is by explaining something called space-time geometry, aka the shape of space-time. What we're going to say is that depending upon mass density, then there are three scenarios, there are three geometries for space-time. So if you have a density that is greater than that of the critical density, that is called a closed space-time geometry, or a closed universe for shorthand. If the mass density of the universe is equal exactly to that of the critical density, we have a flat universe in comparison. And if your density is a little bit less, or just less than the critical density, then we correspond to that an open universe, or we call it an open geometry universe in comparison. The really cool thing is that these three different shapes of space-time, they have very, very bizarre consequences in terms of the fate of the universe. But the first thing that I'll kind of want you to notice here is that ignore the symbol of omega. It kind of deals with the cosmological constant and the mass density ratio. Not super important for us. If you want to read about it, that's fine, but not necessary really for our class. But each one of these three black shapes corresponds to a computer simulation of what the universe would kind of look like from the point of view of an ant, for example. And that might seem kind of weird, but let's think about it this way. When you walk outside, what shape does the earth look like to you? Well, it's wrong, but when you look outside, the earth looks flat. But is the earth actually flat? No, unequivocally no. We learned that back in chapter 2 from the ancient Greeks. The earth is a sphere. But because we are so small and the earth is so large, we don't see that geometry. We don't see the curvature of the earth. It looks flat to us. The same thing is true for an ant on a piece of concrete. A piece of concrete is huge. An ant is very small. So the ant sees the concrete as being straight, even though it might not be straight from our human perception of it. It might be curved, for example. So in a similar way, we are in the universe. We exist in space-time, and it might look like a certain shape to us, but we're a small object in a very large, infinitely large object. But if the universe is closed in geometry, it has a consistency that looks something similar to a sphere. Not actually a sphere, that's too literal, but similar in behavior, in the sense that triangles have very weird shapes, as we'll find out in the next slide. In an open universe, it's more like a horse saddle shape. It kind of has this weird kind of U shape to it here on the kind of top surface. A flat universe, quite boringly, is just a flat piece of paper, end of story. But again, based upon the kind of cosmic microwave background measurements, we're kind of more related to this and not so much this one. We are flat-ish. We're not quite as extreme as this one. This is an extreme case of an open universe. But we're kind of like a hybrid of the two, closer to this one, but still having some openness to its kind of curvature, some saddle-like shape to the curvature of the space-time that we occupy, nonetheless. But even though we don't exist in a closed universe, we're going to go ahead and talk about it nonetheless. And what we're going to say is that for a closed universe, space-time is finite. So that contradicts the cosmological principle. So we're definitely wrong, but if it were true, space-time is finite. So that means that the attractive force of gravity beats out the repulsive nature of dark energy, because dark energy is what powers the expansion of the universe. The more dark energy that exists in the fabric of space-time, the more space-time is going to expand as a consequence. It was kind of part of that circular reasoning that I talked about from before in the first part of this chapter. But what this means is that if you were to take two beams of light and shine them in a closed universe space-time, those two rays of light would converge. They would cross paths naturally because the fabric that they are moving through is converging itself. And because the fabric that they exist in is converging, then they will converge themselves, even if they're parallel to begin with. The really cool thing about a closed universe is that there is no cosmological horizon. There is a finite number of universes. There's a finite number of galaxies in that universe. And if you were patient enough, you could count them all. In that type of universe, what's going to happen is that the universe is going to eventually collapse back onto itself, and it will kind of form many, many, many black holes until they merge together to form a singularity. And possibly that singularity could itself form another Big Bang, form another modern day universe, contract into black holes, a singularity, and then Big Bang again. So this idea of the big crunch, too much gravity, not enough repulsion, turns out. It just basically kind of allows the universe to collapse on itself and possibly kind of reform over and over and over again. It's a very cool idea, but again, based upon sources of evidence like the cosmic microwave background, probably not the one for us, but still an interesting one to talk about nonetheless. The flat universe, we are somewhat flat, close to flat, but technically a little bit open. But for a flat universe, space-time is infinite, which is great because it agrees with the cosmological principle. Two rays of light remain parallel, and we have essentially proved that. Not technically, there is a little bit of a divergence in our measurements, but they're close to being parallel to each other. But basically, what is the fate of the universe? Well, it is eternal. It's just going to keep expanding forever and ever and ever. And one thing that could happen for a flat universe is that as it expands, it's going to be cooling down and cooling down and cooling down until the temperature of the fabric of the universe reaches 0 Kelvin, such that nothing can exist in that universe. It has no energy, so therefore it is cold and empty. We call the Big chill fate, a heat death, because the universe basically freezes out in that case. But the open universe is more interesting to us. With an open universe, space-time is infinite. We basically have too much dark energy, and it turns out that accelerates the growth of the space-time fabric to where it overwhelms the attractive force of gravity, and we bloat too much as a consequence. Kind of like you see right here in this kind of path that we've got in this case. So parallel rays of light, they kind of pull apart naturally because of the saddle shape of the open universe. And based upon some very complicated experiments in space, we've actually seen that parallel rays of light ever so slightly diverge in our experiments. And it's laughable, but they technically do diverge. So that means that our universe, at least on small scales, as we've measured it, is technically ever so slightly open, not perfectly flat, but close to flat in this case. But for a universe like this one, the universe is going to expand forever. And it turns out that there are two possible fates for a universe that's open. A big chill, kind of like for the flat universe, but also something called a big rip as well. And what a big rip corresponds to is it corresponds to a continued growth of dark energy in that universe, and therefore a continued aggressive expansion of that universe, an accelerating expansion of that universe. And therefore, because of that accelerating expansion of the universe, the fabric of space-time will basically rip itself apart, and it will basically break everything apart. Matter will turn back into energy because it's going to be ripped apart at the most fundamental level, and therefore there will be nothing left in the universe except darkness. A little bit kind of dramatic in that case, but still. Now, how likely is this to occur in terms of immediate future? Unlikely. A big rip scenario will take tens, if not hundreds of billions of years to occur. So you're safe, not going to happen anytime soon. But it turns out that an open universe, it really kind of has two fates, the chill and the rip. It depends upon the acceleration of the growth of that universe, the acceleration of the growth of space-time. If the acceleration is increasing over time, the big rip is going to happen. If your universe is growing at a very small acceleration, close to zero, then the big chill is more likely. This is kind of important because we have to kind of, again, go back to Hubble's law. The further away a galaxy is, the faster that it's moving away from us. So therefore, we have an acceleration that's occurring. So we know that our universe is accelerating. So we know that we have an open universe to some extent. But unfortunately for us, by looking at Hubble's law at progressively larger and larger distances, we can actually show that the acceleration of the universe has increased over time, which means that the amount of dark matter, which powers that expansion, has also increased over time. So what that means for us is that we are probably going to we're probably going to have the big chill, but we could possibly have the big rip scenario. But as a last question that I ask you, kind of rhetorically in chapter 29, what is the exact fate of our universe based upon current data? Well, if you're looking at the lecture notes on 9, I leave it as a question mark because I want you guys to watch the video to get the answer. It turns out that our universe is an open one, but it's ever so slightly open. It's more flat than open. So therefore, our fate is probably going to be the big chill. It's going to take tens of billions of years to occur, but our universe is going to keep expanding and keep expanding and keep expanding. And then depending upon some people, which my colleague at Caltech is a very strong proponent of, because the amount of dark matter is increasing, he believes, and this is becoming a slow majority in opinion, is that the amount of dark matter is going to, the amount of dark energy in the universe is going to continue to increase such that the geometry of our universe will change, and we'll have now a big rip scenario. Way too much dark energy, not enough dark matter, not enough luminous matter like stars and galaxies and things of that nature, and therefore will turn into a big rip. So that's the growing consensus, that the big rip is probably what's going to happen. But back when I was an undergrad, the consensus was the big chill, but it seems like we're trending in the opposite direction in modern day times. So evidence points in that direction. So I'll go ahead and change my ideas, chapter 1 style with the scientific method, and say that most likely we're probably going to have the big rip. So what's going to happen is that the space-time that holds everything together is going to keep expanding, and that expansion is going to approach smaller and smaller scales, such that what's going to happen is that it's going to take tens of billions of years, but the distance between galaxies is going to increase because the material that they exist inside of is accelerating in its growth. So they're moving apart from each other, not because they're moving, but because the material that they're inside of is moving. Kind of like an escalator kind of effect. But the escalator accelerates over time, so they're moving away from each other more aggressively. That aggressive motion is going to start to manifest on not galaxy scales, but individual solar system scales, such that individual solar systems within a galaxy are going to start to move apart because the fabric of space that they exist in on these smaller scales is now going to be accelerating in its expansion, in its repulsion in this case. And then that effect will manifest into the individual planets, how far apart they are from each other. So what this means, for example, is that all of a sudden in the nighttime sky, in tens of billions of years, planets are going to look dimmer, not because they're reflecting less light, but because they're further away from the Earth, because the fabric of space that they occupy is growing. Eventually the moon, well, it's already gone at this point, but if the moon were still there, it would start looking further and further and further away from us. It would get smaller and smaller and smaller because the fabric of space that it occupies is now growing and we're growing away from it. And then eventually at that point, we will kind of expand, and that will kind of occur on smaller scales, and then we'll be kind of ripped apart as a result. So the thing is that we're going to go ahead and be ripped apart at the end. Very, very sad. That's it. Thanks for listening, and I'll talk to you guys later.